Hi, everyone. So this video is going to be Chapter 5, Lecture 1. Let me share my screen. So we're going to spend 2 days on this one, 2 lectures. Okay, so Chapter 5 is on Introduction to Solutions and Aqueous Solutions, Aqueous Reactions. So we'll start off with introducing to you what is a solution, and then we'll go into molarity and some solution stoichiometry. Okay, so you guys know, right, when we put table salt into water, it seems like it's disappeared, but it hasn't, right? You know that salt is still there because when you taste the water, it tastes salty. So what actually has happened to the salt? Well, it dissolved, right? And so these mixtures, we call those solutions. So a solution is a mixture between a solvent and a solute. And the majority component is called a solvent. The minority component is called a solute, right? So, in anything, right? Just figure out what the majority component is, that's a solvent, and minority component, the solute, right? So, for example, beer, right? Beer is a solution, and the solvent is water. It's mainly water, right? Because it's only 5% or so ethanol. So ethanol would be the solute. Okay. What's another example? Wine, right? Wine, the solvent is also water. And the solute is still ethanol, right? Because it's 12%. Okay. But once you get to like Bacardi 151, right? Now the majority component is the ethanol. So the ethanol is now the solvent and water is the solute. Okay. So that's just the term, right? That you should know. So any solution where water is the solvent, we call that an aqueous solution. And remember what the symbol is for that, right? AQ. So because solutions are mixtures, it's hard to figure out how much, like, let's say you have a salt solution, right? And you want to know how much salt is in there. It's kind of hard to tell because all the salt's dissolved, right? So the way to describe solutions accurately, so that it makes sense, is to have a concentration, right, of the solution. How concentrated is it? Do I have a lot of the solutes and a small amount of solvent? Then that's a very concentrated solution, right? But if I have a small little bit of solute in a big amount of solvent, then I have a very dilute solution. And so in order to, quantify it, we have to be able to measure, right? And that measurement is called molarity. Okay. So molarity is a way to express solution concentration, and the symbol for it is big M, okay, which stands for molarity. Okay. And to calculate molarity, what we do is we take the moles of solute on top and the liter of the entire solution on bottom. So that makes sense, right? If you have a lot of solute in the same amount of solution, in the same volume of solution, then it's going to be more concentrated, right? This number is going to be higher. So the higher the molarity, the higher the concentration. Okay, so let's go to the board. I have representations here of molarity, right? So remember, molarity, big M is moles over liter. I got 2 beakers here, right? To illustrate molarity. In the left beaker 1, each of these dot represents 1 mole of sodium chloride, right? And the volume here is 2 liters. You guys see that, right? So if you count the dots, 3, 6, 9, 10, that's 10 moles of NaCl per 2 liters, okay? So 10 moles of the solute over 2 liter of the solution. So if you divide this out, right, 10 divided by 2 is 5. So this is a 5 molar NaCl solution, and that's how it would be written. Okay. Now, if we go to beaker number 2, okay, when we do the same thing, right? Moles over liter. Let's count the number of moles. 3, 6, 9, 10. Oh, still 10, moles of NaCl on top over the total volume, right? Which is now 1 liter, okay? So that's equal to 10 molar NaCl, okay? So guess which one is more concentrated? This one, right? Numerically, it makes sense, but also conceptually, right? You have less volume, but the same amount of moles, right? So they're all more clumped together, right? Or more concentrated, right? This one is less concentrated or more dilute, right? So know those terminologies. So this one, of course, is twice as concentrated as that one, okay? And so in expressing molarity, you're communicating how concentrated a solution is. So if you taste beaker 2, of course, it's going to be much saltier than beaker 1, right? Because it's a higher molarity, right? So from now on, you're going to see that, right? When we work with solutions, you're going to see a molarity, okay? And so now you know what that is, right? It's just moles over liter. Okay? But what that allows you to do is now to convert, right? To measure out moles by volume, okay? Obviously, if I want to take 5 moles out of beaker 1, I can't go to the balance and mass it out. Like you've been doing, when you guys were working with solids, you were able to do that, right? You just go and mass it out on the balance to get moles. Here you can't, right? You can't go out and you can't go to the balance. It's in a solution. So you have to measure by volume, okay? So let's say, beaker 2, I want 5 moles out of salt. If I want 5 moles, like let's say I want to drink 5 moles, what volume, right? So the question is, what volume is 5 moles of NaCl? What volume for beaker 2? Okay. So 5 moles of NaCl, and it's 10 molar. So you break it up, right? Whenever you see big M, just break it into moles over liter. It's going to be easier for problem solving because again, you'll know what to put on top and what to put on bottom. So we want liter on top. So 1 liter on top, got 10 moles of NaCl on bottom. So that cancels, and you have half a liter. Okay. All right. So what are we saying? We're saying I have to drink half a liter of solution of beaker 2 in order to drink 5 moles of NaCl, right? Because I obviously can't pick those out, right? It's dissolved in there. Okay. So I have to measure by volume. So I know that since it's homogeneously mixed, if I drink half a liter, I will drink 5 moles of it. Okay. Now, similarly, I can also ask the question, what or how many mole of NaCl are in 0.25 liters of beaker 2 solution? Okay, so my given is 0.25 liters. Okay. And what am I going to put on top now? Oh, the 10 moles, right? Because I want moles out, 10 moles of NaCl over 1 liter. Okay, so that would be 2.5 moles of NaCl. Okay, so that means if I drink a 1/4 liter of this solution, I would drink 2.5 moles of NaCl. Makes sense, right? Okay, so if I chop this evenly into fourths, right? When I drink 1/4 of it, it will be 1/4 of 10, which is 2.5. Okay, so that's how it works, right? That's how molarity works, is to be able to communicate how concentrated a solution is quantitatively, right? So that you can actually be precise in measuring out moles, even though things are dissolved in there. Okay. We can do a couple examples too with beaker 1, right? So beaker 1, it's a 5 molar NaCl. So we need to translate that. Anytime, remember, you see big M, just rewrite it as 5 moles per liter, right? Just right there. So now we can ask how many mole of NaCl are in 1 liter of beaker 1 solution. All right, start with what you give it, 1 liter. All right, use this, right? That's why we break this big M into moles per liter. So again, now we ask ourselves, what unit do we want on top? We're looking for moles of NaCl. So 5 moles of NaCl is on top. And we want liter on bottom. Okay. So that's 5 moles of NaCl. Okay. This makes perfect sense, right? Because you got 2 liters here, and in 2 liters you have 10 moles. So if I drink 1 liter, of course I'm going to drink half. Half of 10 is 5, right? Okay. So this is a new conversion factor for you, right? Molarity. So that's what I would do, is go and practice it. Just like, you know, how you got good going between grams and moles. You're going to do the same thing, right? Try to practice going back and forth between moles and liters using molarity. Okay. So molarity is basically like your new molar mass now, right? Where you can go from a mole of something to something else, right? And back. All right. So back to the slides here. So how do we prepare a solution of a specific molarity? Well, let's use sodium chloride as an example again, right? Let's say you want to prepare 1 liter of a 1.0 molar NaCl solution. So what does that mean, 1.0 molar? It's 1 mole of NaCl per liter, right? So you would grab one of these volumetric flasks, that's exactly 1 liter, right? And then you'd measure out 1 mole of NaCl. Well, what's 1 mole of NaCl? Look up its molar mass, right? Or calculate it from periodic table, 58.44 grams. So you go to the scale and you'd mass out 58.44 grams of salt. And then you put it into, excuse me, you put it into the volumetric flask. And then you add water to the mark, right? So you see this mark right here? That's exactly 1 liter. And then after that, you mix really well, make sure that the salt dissolves. And by the time it's dissolved, it has that exactly 1.0 molar concentration, right? So this is a cool instrument. You guys be using this later. That's the instrument that, or the glassware that you're going to use to prepare solutions. Okay, so now next we're gonna get into solution stoichiometry, right? Last time in chapter 4, you guys learned all about stoichiometry. We did a lot of problems, right? Now we'll continue with that, but instead of starting at grams of A, right, we're gonna start at liter of A solution, right? Because now we're in solution stoichiometry. But you go through, you know, pretty much the same routes, okay? You just have a different starting point, okay? So you're going to be using molarity to get to moles, right? Instead of molar mass to get to mole, okay? So let me show you where we were at with the roadmaps so far. Okay, remember this from last time? Okay. Atoms and molecules of A goes to mole of A through Avogadro's number, and then between mole and gram, right, we have molar mass of A. Now we cross to the other side, right? Stoichiometry. To cross to the other side, we need to be at mole first so that we can use the mole to mole ratio from the balance equation to get to mole B. And then mole B just mirrors mole A, right? You can go to grams B, molar mass of B, or you can go atoms, molecules of B with Avogadro's number, okay? So now we're going to add another freeway, right? We're always adding freeway on top of this every time, okay? So the way I want you guys to think about this is when you have grams of A, it's probably a solid, right? Most likely a solid. So now I'm going to actually put states in here. So the way we're learning stoichiometry is we're slowly learning each state of matter. the stoichiometry by states of matter. So far we learned stoichiometry with solids, and it's easy because you just have a grams and you turn that into mole with a molar mass, right? But now we know solution. So we have another free way. Here, we're going to start from liter of a solution, so A aqueous, right? So again, if you start at grams of A, that's great. That's like just putting it on a scale. It's easy, right? Well, liters of A, you can't go and mass that. So what do you need? You need a molarity, big M of A, to convert from liter of A to mole of A, right? What we just did like a few minutes ago. That's why you need to get good at this now, right? You guys are good at this now. And you're going to do the same thing for this. So again, you can go all over the map, okay? So that's going to mirror on the other side too. Liter of B equals. So to quickly use this roadmap, now it's getting busy, right? Quickly use this roadmap is paying attention to the problem. What state of matter is the problem in? So I know on which part of the map I'm going to be, right? Is it talking about grams or kilograms or pounds? Then I'm here, right? I'm here in this box, right? But if it's like a solution of blah, blah, blah molarity, oh, I'm not here. I'm here now, right? But still, all roads lead to moles, okay? So let's go back to our slides. We're gonna do a couple example problems. All right, so this one here is just straight up, how do you get a molarity of a solution containing 25.5 grams of KBr dissolved in enough water to make 1.75 liter of solution? Okay, this is, pretty straightforward here, right? What is molarity? Moles over liter. So let's get 25.5 grams of KBr to moles, right? And then divide by the liter, right? To get to molarity, okay? Okay, so what we do, we take 25.5 grams of KBr, 1 mole of KBr on top, 119 grams of KBr on bottom. That's the molar mass, right? And then you get 0.21429 moles of KBr. You take that on top, divide by 1.75 liters to get 0.122 molar, right? That's 3 sig figs. Okay. So that one's very straightforward. You should practice more here. Let's do this one. How many liters of a 0.125 molar NaOH solution contains 0.255 moles of NaOH? Okay, so let's go to the board on this one. So a 0.125 molar NaOH. Guys, remember what I said? Anytime that you see big M, you're going to break it down into the units of moles over liter, right? So rewrite it. I'm serious. Every time you see it, right, it's going to help you so much if you rewrite it like this. Because when it's in this contracted unit, it's really hard to do calculations with, okay? So have it like this. And then what are you given? You're giving 0.255 moles of NaOH, 0.255 moles of NaOH. And now what should go on top? What should go on bottom? Because it's asking you how many liters, right? So liters should go on top and 0.125 moles of NaOH on bottom, okay? So you end up dividing here by molarity, right? And that's going to be 2.04 liters of the NaOH solution, okay? Be specific, right? Liters of who? It's the NaOH solution. So in 2.04 liters of the NaOH solution, that's how many moles are inside, right? 0.255 moles of NaOH, right? That's what it's asking. All right, you guys can practice here too, right? Many practice problems for you guys to do. All right, now let's go on to solution dilution. In solution dilution, um, you know, in lab, there's not a lot of space, right? So usually we just make one solution, we call that the stock solution, and it's really concentrated. And then from that stock solution, if we want like smaller molarities, right? Less concentrated solutions, we would dilute it. And how do you dilute anything? Just add water, right? So it makes it simple, right, for storage. So solution dilution has a very simple equation. It is M1V1 is equal to M2V2. So this equation, remember, it's only to be used for dilution. It should not be used for stoichiometry, okay? So M1V1 equals M2V2. M1 is the original molarity of the stock solution. V1 is how much of the volume of the original solution is equal to the molarity 2 times the volume 2. Okay, so basically molarity 2 is your new desired molarity that you want to dilute to, and then how much of that solution do you want is volume 2. Okay, so very simple equation, and everything's given for you to you, and you just have to solve for one variable. Okay, so here's an example. What if we want to prepare 3 liters of a half molar calcium chloride solution from a 10 molar stock solution? Okay, so in this case, we're gonna call 10 molar the M1, right? Half a molar, the M2, and then 3 liters is V2 is given to us, right? So we need to solve for V1, okay? So let's go to the board for this. So we have V1 is 3, M1 is 10 molar. M2, the desired, is half molar. And V2 is given to us as 3 liters. Okay. So what we don't know is V1. Okay. And here's our dilution equation. M1V1 is equal to M2V2. We are solving for V1. So algebra that, guys, V1 is going to be equal to M2V2 over M1. Okay. Now it's just plugging it in, right? V1 is equal to half molar times V2, 3 liters, over M1, which is 10 molar. So notice molar will cancel. And V1 is 0.15, it looks like, right? Let me double check. Yeah, so 0.150 liters. Okay. So what we're saying is we would need 150 mils or 0.150 liters of the original stock solution, right? We put it into a flask that is 3 liters, like a volumetric flask, right? And we fill it up with water, and that'll give us half molar. All right. So that's nicely illustrated here in this picture, right? So once you find 0.150 liter, you put the 0.150 liter of the 10 molar stock solution in there, and then you add water to the mark, right? And that'll be 3 liter, okay? And this new molarity, which is M2, is half molar, okay? All right. Let's do this one together. To what volume should you dilute a 0.200 liter of a 15.0 molar NaOH solution to obtain a 3.00 molar NaOH solution? Okay, so let me write all that down. And now we'll solve it, right? So it really doesn't matter which one you call M1, V1, which one you call M2, V2, as long as you keep them together, right? So here I have the first liter I see, let's call that V1, right? And that's tied to the first molarity I see, so we'll call that M1. And then 3 molar, that's our desired one. Let's call that M2. And so this, what it's asking, what volume must be V2? So we don't know V2. So let's solve for V2, right? From our dilution equation, it's M1 V1 over M2. Okay. So V2 will be M1 is 15.0 molar times V1, which is 0.200 liters, over M2, which is 3 molar. So molar cancels. V2 looks like 1 liter, right? Yep, 1 liter. So what we say here is if you take 0.2 liters of the 15 molar solution, and you put it into a 1 liter volumetric flask, the new concentration would be 3 molar. Okay. So every time you see dilution, guys, you just use this equation, label it, right? You'll always be given 3 things and you're solving for a 4th. So that's pretty straightforward there. Okay, so now let's go to solution stoichiometry. Okay, we have our roadmap up there. Okay, and let's do this problem together. So what volume in liter of a 0.150 molar KCl solution will completely react with a 0.150 liter of a 0.175 molar lead-2 nitrate solution according to the following balanced chemical equation? 2 KCl plus PbNO32 goes to PbCl2 plus 2 KNO3. All right, let's go to the board. Okay, I'm gonna have you guys look at the roadmap one last time here. Okay, so you can see that in this problem, we need to go from, right, liter, right? It asks us what volume in liters. Okay, so we're not in these boxes, right? We're in the liter boxes. So we start at liter of lead-2 nitrate, go to moles of lead-2 nitrate, and we'll go over to moles of KCl, and then the liter of KCl solution. Okay, what volume in liter of 0.150 molar KCl will react with 0.150 liter, 0.175 molar PbNO3 to solution. So 2 KCl plus PbNO3 goes to PbCl2 plus KNO3. And it goes 2, 1, 1, 2 for the balance equation, right? All right, so let's come up with a plan, right? Where do we start? Okay, lots of numbers up here, okay? But where you start is where you have two key pieces of information. Look on your roadmap. In order to get to moles, right? Stoichiometry problems, you need to get to moles. But in order to get to moles, you need to know a volume and you need to know a molarity. So where do you start? Are the numbers that have volume and molarity. So you don't start here because you don't know the volume. It says what volume, okay? So that's how you know where to start. You need to start where you have a molarity and a volume. And then you start at this number rather than this one because it only has 1 unit, right? Molarity is actually 2 units. It's moles per liter. So you always start at the liter, the 1 unit, and then you get to moles. So how do you get to moles? Well, here's molarity. And remember, you can rewrite that as 0.175 moles over liter. Okay. So that means liter should go on bottom, right? And 0.175 moles of PbNO3 goes on top. Okay. So liter cancels. Okay. And then now you go to mole to mole ratio, right? So we want KCl to be on top. So we look at KCl, that's 2 moles of KCl. And then 1 mole of PbNO3 . Okay. And then we need to get to volume, right? Volume of KCl. So again, we have the molarity now of KCl. We need to use that, right? Rewrite the molarity as moles of KCl over liter. And now what goes on top? The liter is going to go on top. 0.150 moles of KCl will go on bottom. Okay. And then calculate. Zero 0.350 liters. 3 sig figs because of that number, right? Of the KCl solution. Be specific too, right? Liter of the KCl solution. Okay, so let's analyze this problem. It actually looks a lot like the stoic problems that you've done before. But instead of using molar mass to get to mole, here you're using molarity to get to mole, right? So you always go to mole first, then mole to mole ratio, and then whatever unit it wants next. So in solution stoichiometry, you start at liter, you go to mole, and then mole of the other thing, and then liter of the other thing. Okay. Okay, let's do this one too. What volume in milliliters of a 0.150 molar HNO3 solution will completely react with 35.7 milliliter of a 0.108 molar sodium carbonate solution according to the following balanced chemical equation? So we have Na2CO3 plus 2HNO3 goes to 2NaNO3 plus CO2 gas plus H2O liquid. Okay. Let me rewrite that on the board, and then we can solve it together. All right. So there, let's make a plan, right? From our roadmap, we're starting with milliliters. So we'll go from milliliters of the Na2CO3 solution, and we need to turn it to liters, right? Of the Na2CO3 solution, and so that we can turn it into moles of Na2CO3, and then moles of HNO3. And then it's asking for what volume in milliliters. So we go to milliliters of HNO3, and then to liters of HNO3. Okay. So let's execute. We have 35.7 milliliters. Okay. Get to liters, divide by 1,000. 1 liter on top. And then use the molarity, right? To get to moles of Na2CO3, you need to use that. But rewrite it. 0.108 moles over liter. Okay. So now it's going to be liter on bottom, 0.108 moles of Na2CO3 on top. Okay. And then we're going to use the mole-to-mole ratio, right? Moles of HNO3, there's a 2 there. And moles of Na2CO3, that's a 1. Okay. And then we get to do liter first, and then milliliters, right? So liters of HNO3 now. We're going to use the molarity here. So rewrite this as 0.105, 0.150 moles per liter. And now we're going to want liter on top, right? So liter on top, 0.150 mole of HNO3 on bottom. Okay. And then back to milliliters. So we need 1,000 milliliters on top for 1 liter on bottom. Okay. That's equal to 51.4 milliliters of the HNO3 solution. Okay. All right. So we've done a couple problems now, right? Again, you need to go and practice this. So make sure you're comfortable going between moles and liter, right? Using molarity. And then this will just seem a lot easier. It might seem hard right now. That's because you're new to molarity, right? So practice back and forth, going between moles and liters. But it's just the same thing, right? Just using the mole-to-mole ratio to go from mole A to mole B, and then using molarity to go back to volume. All right, let's go back to the slides. Okay. Next topic we're going to go into is solubility. Okay. So solubility talks about how much a solute will go into a solvent, right? So we know, if you stir salt water, or if you stir salt into water, after a while, it won't dissolve anymore, right? Because it will hit its solubility limits. Okay. So we need to know what happens when a solute disappears, right? To kind of understand why, you have this solubility limit, all right? So what happens when a solute dissolves is you have two types of interactions at play. You have the solvent-solute interactions, and you have the solute-solute interactions. So what happens is the solvent has to be attracted to the solute in order for you to have dissolution, right? In order for you to have things to dissolve, they need to be somewhat attracted to each other. Okay. So we'll just talk really briefly about this. We'll go more into detail in the later in the semester. But basically, the water molecule is polar, and what that means is the oxygen end of water, this one right here, the fatter atom, is more negative. It has a partial negative charge on it, and the hydrogen has a partial positive charge on it. So water actually has these poles, and so the negative end of water attracts a cation, and the positive end of water will attract an anion. Okay, so you see in this picture, the delta negative end of water will go for the sodium plus, right? And the hydrogen end of water is going to go for the chloride. And it's going to pull that ionic interaction apart, right? So that you no longer have the crystal lattice. So why do we see salt as a solid? It's because of that crystal lattice, right? Remember that plus minus interaction? Now water goes in between and separates those. So that's why it looks like the salt has disappeared, right? It hasn't, it's just solvated. That's what we call it, right? Because the water has come in between the sodium plus and the Cl minus, and now we don't see it as a solid anymore, right? So here's the bigger picture, right? Here's your crystal lattice of sodium chloride with plus minus, and water comes in between. The delta negative end of water picks up the cation, and then the hydrogen end of water picks away the negative. And so it's just picking apart the crystal lattice, right? And that's what dissolving is. Let's talk about electrolyte and non-electrolyte solutions. So materials that dissolve in water to form ions will conduct electricities. And so these are called electrolytes. There are materials that will dissolve in water, but it won't be charged, right? It won't give ions, so therefore it won't conduct electricity. So these are called non-electrolytes, right? So for example, if you put electrodes that's hooked up to a light bulb into a salt solution, it will light, okay? Because you have ions in there where electrons can move, okay? And so the word electricity, right, comes from movement of electrons. So if you have ions in solution, you're able to conduct electricity because you're allowing electrons to move through the solution, right? Electrons will be attracted to the positive ion and repelled by the negative ion. So that will give movement of the electron. But in a sugar solution, right, there's no charges. So the light bulb is not going to light because the electrons can't move, right? So there's no electricity, okay? So it won't conduct. So we call that non-electrolyte. We also have terms like strong electrolytes and weak electrolytes. What that just basically means is how much ions is in there, right? The higher the ion concentration, the stronger the electrolyte. So sodium chloride, for example, is considered a strong electrolyte because it dissociates completely and gives a lot of ions. Whereas like weak acids, like acetic acid and vinegar, it only dissociates partially, right? Only a few percentage of it dissociates. So it doesn't have a lot of ions. And so therefore, we call this a weak electrolyte. Okay. So here's a picture of a sugar solution, right? You don't see charges, right? Because the sugar molecule is not ionic. It's covalent, so it's not going to break up into ions, right? So covalent compounds that dissolve in water are non-electrolytes. Ionic compounds that dissolve in water are electrolytes, okay? All right, let's talk about acids. So acids are molecular compounds that ionize when they dissolve in water. And we talked about this briefly, right? So acids that ionize 100%, we call that strong acids, okay? So an example of that is HCl, right? So hydrochloric acid will dissociate into protons, right? Remember, proton is a hydrogen that has lost its electrons. Okay, so it dissociate to form H plus and Cl minus, okay? 100%, okay? So if you have 100 HCl, you will also create 100 H plus and 100 Cl minus. Whereas weak acids like HF will only dissociate partially, meaning only a small percentage of it would dissociate, right? So HF, for example, is probably only about 3% dissociation. So HF, if you have 100 of those, only about 3 will become H plus and F minus, okay? Okay, so let's practice writing dissociation and ionization equations because we're going to need this to go on to the next part. Okay, so I'll switch over to the board and we're going to practice dissociation. This word just means that things will split up to become their ions. And what things? Ionic compounds, right? Because ionic compounds are the ones that are charged. So for example, do you see that sodium sulfide, right? Na2S, that's definitely an ionic compound, right? Because you have a metal, non-metal. It's gonna become what? 2 sodium plus and 1 S, 2 minus, and 1 sulfide, right? So all you need to do is just split these up into ions, okay? The 2 tells you that there's 2 sodiums, right? So sodium plus. Okay, now if you have polyatomic ions, you don't split the polyatomic ions, right? You guys know that now. So it just stays together. So Na2SO4, to write the dissociation reaction, you just go 2 Na plus aqueous plus SO4 2 minus, right? The 2 comes from this little 2, right? It tells you there are 2 sodium plus in there. So that's what you write. You write 2 sodium plus SO4 2 minus. And then for acids, when you see acids, you also dissociate it, right? So the protons, remember, protons are positively charged, right? And then you have the anion there. So you split that up. You see 2 protons here. You go 2 H plus aqueous plus SO4 2 minus aqueous. Okay. All right. So let's practice some more on the board. Okay, what if I have CaCl2 aqueous? So CaCl2 aqueous, we look at it, what looks like an ionic compound. Why? Because you got metal, non-metal, right? So now just split it up. Calcium is in group 2A, so calcium is 2 plus, right, aqueous, plus there's 2 chlorides, right? So 2 chlorides. All right. So basically what this picture looks like is I have calcium 2 plus, and I got a chloride, and I have another chloride, right? That's what it's saying, right? These are just swimming in solution, right? Because the water came between and dissolved it, right? Aqueous. Okay. So when you see aqueous, that's what it means. You split it up into its ions. Okay. Let's try another one. H3PO4, aqueous. You see there are 3 protons, so it's going to be 3H plus, aqueous, plus a PO4, 3 minus, aqueous, right? That's a phosphate. You guys know that, polyatomic. And let's see what else. Strontium. Phosphate. Okay, let's break that up. There are 3 strontiums, right? And strontium's in group 2A, so we know it's 2 plus. And then how many phosphates are there? There are 2 phosphates, or phosphites, sorry, right? PO3. So 2 PO3, 3 minus. Okay. And that balances out, right? 6 plus and 6 minus there. Okay. Let's see what else we can do. How about iron 3 nitrate? Aqueous. Right, all these are going to be aqueous. So anytime you see AQ, okay, split it up. So it'll be Fe 3 plus aqueous plus 3 NO3 minus aqueous. Right, where does the 3 come from? Here. There are 3 units of nitrates, right? So 3 NO3 minus. How about this one? Cobalt 1 sulfate. So we know it's cobalt 1, right? Because sulfate is 2 minus. And so you got 2 cobalt. So each cobalt must be 1 plus. So you go 2 cobalt 1 plus, which is plus, aqueous plus SO4 2 minus. Okay. All right, so practice that, guys, right? Writing this dissociation reactions. Anytime you see aqueous, right, you just split these up into their ions, right? Ionic compounds are made of the positive, and something negative, right? And we're just showing that here. Okay. And this is actually a better representation than this, right? Because when you write it like this, they're stuck together as if they're in the crystal lattice, right? Well, it says aqueous. The crystal lattice is gone, right? And so this is a better representation to show that it's in solution, it's dissolved, and it's swimming around, right? It's not stuck in a crystal lattice, these ions. Okay, let's go back to the slides. Okay, now let's talk about the solubility of ionic compounds. So it's really hard to predict solubility. Now, even experts cannot predict solubility of ionic compounds that well. So for example, NaCl, which is sodium chloride, right, dissolves really well in water. But silver chloride, AgCl, right, you just replace that metal of sodium to silver, and all of a sudden it does not dissolve in water. Okay. And it's kind of hard to explain why, right? And so we just have solubility rules, okay, for which ionic compounds are going to dissolve in water. Okay. So this is a table that you guys get to have, and it's on Canvas, so you can actually print this out, okay? Or ask me for one. I can print it out for you. What you get to have this on exams and quizzes, but you need to know how to use it, okay? So do you see there are 2 columns? Okay. There are 2 columns, and then there are 2 rows. Okay. So the top part, it says compounds containing the following ions are generally soluble. Okay. And so it gives you the one that are generally soluble, but then you can't forget to look at the exception, right? And so, for example, all of these are soluble, no exceptions. But then when you go to chloride, bromide, and iodide, they're generally soluble except for when they're paired with silver plus and lead 2 plus, then they're going to be insoluble. Sulfate is generally soluble, but when paired with these, it's insoluble. Okay. And then at the bottom, it says compounds containing the following ions are generally insoluble, right? So hydroxides and sulfides are generally insoluble except for when it's paired with these metal ions. Okay, so you have to watch out for that, right? Carbonates and phosphates are generally insoluble except for when they're paired with lithium plus, sodium plus, K plus, and ammonium plus, right? So then they would be soluble. Right? So let's go and practice this. All right, we can practice predicting the solubility here. So for PbCl2, I'm going to try using the marker here. Give me 1 second. All right, so for PbCl2, okay, so look at that solubility chart, right? And try to determine whether that is soluble or insoluble. So go ahead, have a peek. All right, so PbCl2, okay, we were like chloride. Okay, chlorides are generally soluble, but then there's the exception. Oh, lead's on there. Okay, so you're going to say PbCl2 is insoluble. And to say that, you got to write solid. Okay, so if it's insoluble, it'll stay in the crystal lattice, right? As PbCl2. Sorry, that's PbCl2. And it'll be a solid. Okay. So now we do the same thing with copper 2 chloride, right? So chloride is generally soluble, okay? Oh, but copper doesn't appear on the exception list, so we're going to write AQ. AQ means soluble, okay? So aqueous, right? Means soluble. All right, let's look at C, calcium nitrate. On our chart, nitrates are generally soluble, no exception, right? And so it's also aqueous. Put AQ. Okay. Now we go to barium sulfate. Sulfate, generally soluble. Oh, but barium's on the exception list, so it's insoluble. If it's insoluble, everybody, we're going to put solid next to it, okay? All right, does that make sense? All right. Let's go to the next ones. Nickel sulfide. Sulfide is generally insoluble, and nickel is not on the exception list, so it's insoluble, and we put S. Magnesium phosphate. Okay, phosphates are generally insoluble, and magnesium is not on there as our exception, so solid. Okay, lithium carbonate. Okay, let's look at carbonate. It's generally insoluble, but when it's paired with these ions, it is soluble. So lithium, right, is in the exception list. So lithium carbonate is aqueous. Last one, ammonium chloride. Ammonium, generally soluble, and there's no exceptions. So aqueous, right? Okay. That's how you do it, right? So the states of matter. So if it's insoluble, put solid next to it. If it's soluble, put AQ next to it. Okay. All right. Okay, so now to our next topic and last topic as well for this lecture, precipitation reactions. So precipitation reactions are when a solid will form when we mix two solutions together. And the insoluble product is what we call the precipitate, right? So here's a great example of that. Okay, you have two solutions here, and it's shown in the picture, right? You have the solution in this flask, and that's potassium iodide, okay, which is completely soluble. And then the flask in the hand is lead 2 nitrate, which is also completely soluble. Now, when you mix those two solutions together, all of a sudden, what do you see here? This yellow solid comes out of solution, right? And that yellow solid happens to be lead 2 iodide. So if you look at your solubility chart again, right? How can we identify that this solid is actually lead 2 iodide? Well, iodide is generally soluble except for when paired with lead 2 plus. And so that's why lead 2 iodide is insoluble. And so that's how we know this yellow stuff is the PbI2. The other product, KNO3, is soluble, okay? And so therefore it stays in solution, right? It's aqueous, okay? So these types of reactions are pretty interesting, right? Where, you know, two totally soluble solution mixed together and you get this solid. And so that is the mark of a precipitation reaction, okay? If you don't see a solid, then you write no reaction here. If both of these are aqueous, then you will not see a precipitate and you would have no reaction, okay? So here's an example of that. When you mix potassium iodide together and sodium chloride together, you'll get no reaction because one of the products would be potassium chloride and sodium iodide, which are both soluble, right? KCl is soluble and NaI is soluble. All right, so let's talk about how to write precipitation reactions, okay? I have to remind you guys about the double displacement reaction, which I showed you in lab one time. But let's review that real quick. All right, let's review that double displacement reactions, right? So precipitation reactions fall under this category, okay? So generally what you have is AB, which is a couple, an ionic couple, right? Ionic compound, plus minus. And you react it with another one, an ionic compound, okay? And then they swap partners, right? So A can't go with C because they're both positive. So A has to go with D, right? So A, D, that's plus minus, and then plus the C, B, plus minus, okay? So really predicting the products for precipitation reactions or double displacement reactions is really easy, right? There's only one way you can swap. Okay, so you just go A, you know, the plus has to go with the new minus, right? And vice versa. Okay. So in precipitation reactions, you have to have a solid, right? One product must be a solid. Um, so here's an example. Let's go back to the slide for a second. Okay, and let's do this problem together. Write an equation for the precipitation reaction that occurs, if any, when solutions of potassium carbonate and nickel 2 chloride are mixed. All right, so again, practice at translating, right? Translating this to a chemical formula. Potassium carbonate is K2CO3, and it says aqueous, right? Plus nickel 2 chloride. So that would be NiCl2 aqueous. All right, so to predict a product here, guys, again, I double displacement. So there's only one way to do it, right? The potassium has to go with the chloride, okay? So potassium is plus and chloride's minus, so you just get 1-to-1 KCl. Now then you use your solubility chart to see what state that should be. Okay, so chloride is all soluble. Okay, and K is not on the exception list, so this is aqueous. Plus nickel carbonate, right? So nickel here is 2 plus, remember that, right? Because here's you have 2 chloride. So nickel here is 2 plus, and carbonate's 2 minus, right? So that's just 1 nickel and 1 carbonate. Okay, then you look here, it says carbonates are generally insoluble. Nickel's not on the list. So it's going to be a solid, okay? So do we have a precipitation reaction here, guys? Yes, because you do have a solid product. Okay. And now you balance, right? So to balance here, most complex, I put a 2 in front of KCl. And then that should be it, right? 2 potassiums, 1 carbonate, 1 nickel, 2 chlorides. Yep. Okay. All right, let's go back to here. Awesome. Let's do this one. Write an equation for the precipitation reaction that occurs, if any, when solutions of sodium nitrate. So sodium nitrate, we're going to translate that to NaNO3, right? Aqueous, plus lithium sulfate. Lithium's 1 plus, right? And sulfate's 2 minus, so it's Li2SO4. Okay, yeah, should be good at that by now. Okay, now let's go and predict the products. Okay. Again, right? The positive has to go with the negative here. So we have sodium sulfate. What is the formula for that? Na2SO4. We look it up. That's yep, that's aqueous. And then lithium nitrate, which is also aqueous. Okay. So do we have a solid here? Nope. So we cross this out because we just write no reaction. Okay, we don't have a reaction. Okay, so we don't even need to worry about balancing it, right? Just say no reaction. Okay, you only have to balance it and go through all that when you actually have a reaction. Okay. Okay, so you guys should practice some more. We're gonna go ahead and move forward to ways of representing aqueous reactions. So far, like what we've written here, these are called molecular equation, right? So here's an example on this slide. This is a molecular equation because everything is written together, right? As far as like the KOH, right? MgNO3 2, like they're written as if they're molecules, okay? But we know they're actually not in their crystal lattice because they're aqueous, okay? So it's better to write what's called complete ionic equations to be more accurate. And to write complete ionic equations, every time that you see AQ, you split it up. Remember when we wrote dissociation reactions about 15 minutes ago, right? When you see aqueous, now you're going to split it up into ions, okay? And if you see solid, you just leave it alone, okay? So this is called a complete ionic equation. So how do we do that? Okay, so KOH, right? 2KOH will become 2K plus 2OH minus. MgNO3 2 will become Mg2 plus 2NO3 minus. Goes to, and this is aqueous too, right? So you break it up as well. 2K plus and 2NO3 minus plus MgOH2 solid. So you just leave that one alone, okay? And now you see these blue arrows, what they're pointing towards are called spectator ions. Spectator ions, they don't do anything in the reaction, as in they started out aqueous and they still stayed aqueous. So nothing happened to them, right? And so that's why we call these spectator ions, okay? And so we can actually cancel these out because they don't do anything. And what's left over would be called the net ionic equation, okay? So we'd cancel out on both sides things that are the same, right? Just like in algebra. And then we write what's left, which is 2OH minus aqueous plus Mg2 plus aqueous goes to MgOH2 solid. Okay. So let's do examples here. Okay, we got two examples here. Let's do A first. I'm gonna write it on the board first, and then we go through molecular, complete ionic, and net ionic equations together. Three SR2 plus 2 LI3PO4 aqueous goes to SR3 PO2 solid plus 6 LiCl aqueous. All right. So we need to see, okay, the equations balance, right? That's good. And this we call the molecular. Okay. So to write the complete ionic, okay, we separate, right? Separate these into ions. But we also have to make note of the coefficients as well. So that's 3SR, right? So 3SR2 plus aqueous plus, there's 6 chlorides here, so 6Cl minus aqueous plus 2 times 3 is 6 lithium plus 2 PO4 3 minus aqueous, right? All the aqueous, what we're doing is we're just splitting it up, right? That's why we were just practicing dissociation reaction before. We go to the right side, solid, so we keep that the same. And here we have 6 lithium plus aqueous, right? This aqueous, so we'll break it up. 6 chloride minus aqueous. Okay. All right, so you see what we did, right? So if you have to, try to work this out, pause the video, try to work it out how I got those, right? Just splitting things up. Now for the net ionic, we're going to cancel things out that are the same. Okay. So on both sides, what do you see that are the same? 6 chlorides aqueous and 6 lithium aqueous. So what do we have left? 3SR2 plus aqueous plus 2 PO4 3 minus aqueous goes to SR3 PO4 2 solid. All right, so the net ionic is clean, right? It has no spectator ions. And a lot of times they will ask you to list the spectator ions. So what is it? Chloride and lithium plus as your spectator ions. Okay. So you guys should know that, right? You guys should know how to write the molecular, the complete ionic, and the net ionic. So it's going to be the same every time, right? The complete ionic, aqueous, split it up into ions. For the net ionic, cancel things that occur on both sides that are the same, and that will leave you with the net ionic, okay? Okay, let's go on to the next one. B. Copy that down. HC2H3O2 aqueous plus KOH aqueous goes to water liquid plus KC2H2O2 aqueous. Okay. All right, so in this case, this molecular reaction is not a precipitation reaction, right? Because you don't have a solid. But this is an acid and a base reaction. Okay, so KOH is a base here. All right. So you make water. Okay. So liquid as well. Whenever you see liquid, just like solid, don't split it up. So when we write the complete ionic equation, it'll look like H plus, right? It's the acid. So remember, it leads with H, right? But that's the proton. So H plus the C2H3O2 negative, right? The acetate ions negative, aqueous plus. The KOH is aqueous, split it up. K plus OH minus goes to water. It's a liquid, so leave it the same. Plus this one's aqueous, so split it up. K plus aqueous plus C2H3O2 negative aqueous. Okay, you see how we get the complete ionic equation? And then we go to the net ionic. Okay. Cancel things that are the same on both sides out. Acetates K plus, and then we'll have H plus aqueous plus OH minus aqueous goes to H2O liquid. Okay. Spectator ions. K plus and C2H3 minus. Okay. So very similar to last time, right? You do that every single time. Anytime you see aqueous, right, you split it up. Okay. Okay, let's go back to the slide. Okay, let's do one more practice problem with this one. Okay, so remember, this is the one we did earlier, but we only did the molecular formula. We didn't do complete ionic and net ionic. So I want to go back and do that one more example for you so you guys see how it's done, right? And then after that, you just got to practice, right? And a lot of this is hard if you don't know your polyatomic. So it's all about that, okay? So potassium carbonate, so molecular. Molecular potassium carbonate is K2CO3 aqueous plus the nickel 2 chloride, so NiCl2 aqueous. Okay, so that's all it gives you. Okay, so sometimes this is all that's given to you, but you know how to predict the product. So go ahead, right? You're gonna do the swap. KCl is aqueous, right? Use your solubility chart. And then NiCO3, you're going to use solubility chart. It's insoluble. Okay. So we do have a precipitation reaction here. Okay. So once you predict the products, right, then you balance the equation. So let's see. Put a 2 here, right? And that should balance the equation. Yep. So we got our molecular, that's balanced. Only then do you go on to do the complete ion. Okay. So C aqueous, split it. 2K plus aqueous plus CO3 2 minus aqueous plus Ni2 plus aqueous plus 2Cl minus aqueous goes to 2K plus aqueous plus 2Cl minus aqueous plus NiCO3 solid. Okay. So the only thing I don't split up is the precipitate, right? Yeah, because it makes sense. It's not aqueous, right? It precipitated out. And then the net ionic, when you cancel things that are the same on both sides, so this goes away, 2K plus goes away, right? And what do you have left? CO3 2 minus aqueous plus Na2 plus aqueous goes to NiCO3. So, okay, so the net ionic is just really clean. It just shows you the reaction, right? These two things came together to precipitate, right? Aqueous to solid. And then the spectator ions are the ones that you crossed out. So if you're asked for that, you'd say K plus and Cl minus are my spectator ions. Okay. All right, guys. So that's it. That's all we're gonna do for this lecture. Okay, make sure you practice that. That's definitely gonna be on the exam. So just go through a bunch of double displacement reaction, okay, and learn how to write molecular, complete ionic, and net ionic. All right. All right, I'll see you guys next time.